Welcome, everyone, once again to Photonics for Quantum 2. I'm your host, Don Feiger, broadcasting live from Rochester, New York, near RIT, but not quite there, at an undisclosed location in my bunker. And we have an excellent week of talks this week. And continuing on from yesterday's talk, which was by someone from Nick Menicucci from Australia, we're back on our 1 p.m. Eastern Time schedule for the remainder of this week. And we also have an impromptu sponsor talk today, which wasn't in the program, but we're happy to have this sponsor give a talk. And we thank all of our generous sponsors whose logos surround me. And due to their generous contributions, we're able to deliver this content for free to you. As you know, you can access the talks later on in the recordings that you see when you expand the accordion after clicking on the name of the talk or the name of the author. And at that location, you can also get the slides. So without further ado, I give you to Katya Seal of Quantum Design, one of our sponsors. Take it away.
Hello, this is Katya Seal from Quantum Design. There are 4 product categories I will mention today: our magneto-optical cryostat, our lithography offerings, our single photon detectors and counting electronics, and our tools for quantum education. Quantum Design is well known for our flagship products used for transport measurements at high magnetic fields and low temperatures, the PPMS and MPMS. We have over 2,000 systems worldwide. We now offer a magneto-optical cryogenic platform, the OptiCool, with a unique magnet design that allows for unrivaled open access to a large sample space. It has 8 optical ports, 7 Tesla magnetic fields, a helium-free cryostat which goes from 1.7 to 350 Kelvin, and low vibrations of less than 10 nanometers. There are over 80 electrical interconnects for user-defined measurements, making for a versatile experimental platform with several add-on options. I will now talk about products that we distribute. The ML3 Direct Write Laser Lithography System from Durham Magneto Optics has feature sizes of 0.4 microns and upwards, with several exposure wavelength options and a user-friendly interface. The innovative NanoFraser nanolithography system uses a heated AFM tip to write directly into a resist, providing fine features of less than 10 nanometers with 3D feature control and excellent overlay precision, all while circumventing beam damage to surfaces. The heated tip writes on the forward raster and the cold tip reads on the backward raster, providing on-the-fly metrology and pattern optimization. Writing speeds are comparable to e-beam litho with many pattern transfer options, as shown in these 2D and 3D examples. Our superconducting nanowire single photon detectors made by Single Quantum use a closed cycle cryostat which can operate continuously for 10,000 hours or more. These nitride-based SNSPDs use a robust fiber coupling technology. They have efficiencies of more than 90%, outstanding timing jitter of less than 15 picoseconds, and high count rates of 100 megahertz or more. We also offer broadband detectors and SNSPDs coupled to spectrometers with several upcoming advancements. We offer photon counting modules made by Q Tools with excellent jitter specs of 2.3 picoseconds RMS and 100 megahertz count rates. Q Tools also makes teaching tools for education, quantum entanglement, and quantum sensing. The QNV demonstrates quantum sensing using diamond NV centers, a light source and detectors, a microwave sweep field, and software to acquire and plot the ODMR curves. The QED entanglement demonstrator has a source of entangled photons and APD detectors. Counting electronics in the control unit allow external data acquisition or direct plotting of key quantities so that experiments like violating Bell's inequality can be performed. There are 4 add-on modules: the Michelson interferometer, the Hanbury-Brown twist, the Hango-Mandel, and the QKD. Together with the add-ons, dozens of experiments are possible. We also offer a motorized version that allows for lab courses to be performed and offered remotely. A more plug-and-play version of the QED, the Quantum Coffer, is catered more towards non-physics majors and the general audience. Here, the entangled source and detector are under the breadboard, and light is guided above it with periscopes. Thanks for listening, and please visit our website or write to us at info@qdusa.com.
Okay, Katya, thanks very much for that presentation, and thank you to Quantum Design for their generous sponsorship of Photonics for Quantum. And some of the material that you just showed is related to today's main talk. Our speaker is Michael Fox from University of Colorado at Boulder, and he'll be talking about education for the quantum revolution. Michael, take it away.
Hello, can everybody see that?
I can see your slide, and we can see your video and hear you.
Brilliant, thanks Don. So hello, my name is Michael Fox, and in this presentation, I will give you an overview of our study into the role of higher education in preparing for the quantum revolution. This talk is based on work that I've done with Ben Zwickel and Heather Lewandowski, looking at the skills and knowledge that exists in and are needed by the quantum industry. Today, I'm going to summarize the results from our paper on the quantum industry, answering specific questions that we hope will be of interest to this audience. By scanning this QR code on the right, you can access the preprint of our paper that's available on the archive, which is also given in the URL there. That has a lot more detail in it than I can give you today, but hopefully I'll pique your interest. So the first thing that I want to talk about is brief motivation for our work. Then I'll describe what the quantum industry is, so that we're all on the same page. Then I'll briefly detail our methodology for data collection, and then present our 5 research questions. The first of which is, what are the career opportunities in the quantum industry? Then what skills are valued, both broadly across the industry as well as for specific roles? Then the next question is, what are the routes into specific jobs, where we look at the degree subjects and levels of existing employees and how they got into the industry. The fourth question is, what new training is needed? This is looking at what new courses and programs might be needed. And then the final question is, what are the hiring challenges that the industry is currently reporting that they face? And then I'll end with a brief discussion and conclusions. So first of all, the motivation for our work. So apart from an academic interest in what the quantum industry is, the motivation is the National Quantum Initiative Act, which was signed into law in December 2018. This act has a number of purposes, but the first purpose is to expand the number of researchers, educators, and students with training in quantum information science and technology to develop a workforce pipeline. In this aspect, higher education institutions are already and will continue to play a key role. This is not only in the research side developing these technologies, but also in training that workforce. As a result of the National Quantum Initiative Act, many universities have set up or are planning to start degree programs or certifications in quantum information science in order to meet the demand from industry for more qualified employees. However, due to the youthful nature of the quantum industry, there does not exist very much detailed information about what skills and knowledge are needed by companies. All that information is hard to find. This is where we hope that our work at least starts to fill that gap. So this brings us to the first question, which is, what is quantum information science and technology in this context? And that leads us into the question of what is the quantum industry? So what is the quantum industry? So the National Quantum Initiative Act defines quantum information science as the use of the laws of quantum physics for the storage, transmission, manipulation, computing, or measurement of information. Note that this does not include the technology part, which is how these systems are physically realized. We have then defined the quantum industry as all companies engaged in activities that either apply quantum information science for their product to function or provide technology that enables such a product. And within the quantum industry, we've identified 5 distinct types of activities. These are broad categories, mainly associated with the types of products that these companies are developing. So these are quantum sensing, quantum networking and communication, quantum computing hardware, quantum algorithms and applications, and facilitating technologies, which includes laser, vacuum, and cryogenic technology providers. Note here we've divided the quantum computing into 2 activities, hardware and algorithms and applications, as these activities are distinct enough that companies may only be involved with one of those activities. Now, while the use of products is significantly different between these different activities, there are similarities in the skills needed, and those are dependent on the technology chosen to implement the product. So one example of this is the technology of ion trapping can be used both for quantum sensing and in quantum computers. But quantum computing can use ion trapping, but that's competing with different technology, which is superconducting qubits. Now, in terms of the methodology that we chose to use, we interviewed 21 companies from across the quantum industry to ask them about the skills and knowledge needed to work in their companies. The red columns on this graph show the numbers of companies who had activities in each of the different categories that we identified. A single company here may have more than one activity, hence why the numbers on the red columns do not add up to 21. So the example here would be a quantum computing company that is also doing algorithms and applications, so that would appear in both columns there. So the recruitment of these companies to complete interviews was made initially through the Quantum Economic Development Consortium. We show in the distribution in blue the companies from the QEDC at the time of February this year to illustrate the distribution from which some of our samples collected. Though we expanded the scope of our research beyond the QEDC through snowball sampling, and as you can see, we successfully managed to sample broadly across the activities within the quantum industry. So just returning back to our outline, I've just given a brief background for this talk, and now I'm going to discuss the findings of our research. So what are the career opportunities in the quantum industry? Now, while different companies gave their employees different job titles, we collated these into the following job types. The height of each bar here indicates the percentage of the 21 companies interviewed that employed at least one person with the job title. Of these, we've identified 5 key technical jobs. These are engineers, experimental scientists, theorists, technicians, and application researchers. Furthermore, we've broken down the largest group here, which is that of engineers, into their specializations, so electrical, software, mechanical, and optical engineers, as well as other types of engineers who often had, and these people often had bachelor's or master's degrees, but many of them had a number of years of additional experience. The second most common job type, was the experimental scientist, who often had PhDs in AMO physics and quantum physics. We also note the job titles of experimental scientist and theorist here highlight the close relation of the quantum industry to academia, as many companies are still in a research and development phase. Though the increase in prevalence of engineering roles indicates this is moving rapidly towards the realization of these technologies. The application researcher role is specific to quantum computing and algorithms companies, as these people interact with the clients to determine if their problems could be solved more efficiently using a quantum computer. So then we now move on to our next question, which is what are the skills valued by the quantum industry? So as the quantum industry covers a wide range of different activities, it is difficult to establish specific skills that are valued across the industry. Therefore, we're going to provide two levels of analysis of the data we gathered from our interviews. The first is just ranking the skills that are shared across the industry, while the second breaks those down by job type, which provides a finer grain size as to where specific skills are needed. So this is on the broader scale. We see that one of the skills most companies reported valuing in their employees was that of coding. Note that this is not coding a quantum computer, but rather classical coding in that sense. So this code would be used to perform physics calculations, for example, while designing a machine, or actually controlling a machine while it's running, to the analysis of data collected from the machine. And coincidentally, the joint top rank skill was knowledge of and experience using statistical methods for data analysis, which is very important when you interpret data from a machine, especially, for example, from a quantum computer, where you have probabilistic outputs. Then 81% of companies reported valuing laboratory experience, such as the ability to set up an experiment, take and record data systematically, or experience with specific hardware setups. The preponderance of the appreciation of this skill highlights the hardware focus of the industry at this moment in time. Similarly, the next three skills of electronics, troubleshooting, and knowledge of material science are all highly indicative of the concrete nature of current work in the quantum industry. Furthermore, all the above mentioned skills and knowledge are classical skills in the sense that they don't necessarily require knowledge of quantum information science, though some may need some knowledge of quantum mechanics when you're considering, for example, semiconductor electronics or material science. The most highly ranked quantum information science skill, and this is in terms of numbers of companies reporting that some employees needed this knowledge, was that of quantum algorithms. This is partly due to the large number of quantum computing companies in our sample, as well as the industry as a whole. The nature of this knowledge varies from knowing the set of existing quantum algorithms and being able to apply them, to being able to come up with new quantum algorithms, or having an understanding of how to apply a series of gate operations on a specific hardware in such a way to optimize the use of that particular type of qubit. So as you can see, these categories presented here are very broad and do not particularly give much insight into what the specific nature of each commonly valued skill is for each company or job role within a company. Therefore, we must look at how each skill is associated with the different job types. So, one of the key outcomes of our work has been the identification of the skills that are associated with each job. In our paper, we describe these in rich detail, but here I'm just going to give you one example because we don't have time to go through them all. This is the description of the skills required by an electrical engineer. The N is the number of companies from our sample that reported they employed at least one electrical engineer. And the skills I would like to highlight that were valued by 38% of these companies were the design and manufacture of microwave circuits that are used to manipulate qubits in superconducting hardware, as well as radio frequency circuits to probe atomic transitions. This level of depth is provided in order to demystify the work that is being done in the quantum industry so that policymakers, instructors, and students have a better idea of how the industry itself functions. For more details of the skills required by the different job types, I refer you again to our paper. In addition to providing a breakdown of skills for particular jobs, we also organize the skills in a manner that may be more suitable for lecturers and instructors who are considering how the skills needed in the quantum industry fit into their own courses. In our paper, we provide skills tables organizing the skills into different courses. Now, this is a subjective choice on our part, so there might be some overlap between these. These different courses we've come up with are traditional quantum theory, quantum information theory, real-world quantum information theory, which I'll explain more in a second, hardware for quantum information, electronics, mechanical engineering, and optics and optomechanics. And just to show you one example, I've chosen the real-world quantum information theory table, which is shown here on the right, which is running quantum algorithms on real hardware. And I'll highlight here the skill of troubleshooting. With quotes from our interview study, we see that quantum coding is totally different from debugging classical code, because classical codes you can step through, and quantum codes you can't do that because you'd have to measure, and when you measure, you just throw your information. So here we've matched up the skills with specific quotes from our interviews to provide context. And it's these kinds of insights that we believe will be valuable to the physics, engineering, and computer science communities when developing new course materials, in constructing that direct link to the skills desired by the industry. So now we move on to our third question. What are the routes into specific jobs? And we attempt to answer the question of what the routes are into the quantum industry by considering what degrees current employees have, and use this as a proxy initially for how these employees gain their skills. However, I would like to emphasize here that this does not imply that students who complete these degrees are fully equipped with the skills to enter the workforce, and indeed many need on-the-job training in order to get up to speed. We see from this plot that almost all companies say that they employ at least one PhD physicist. There are two overarching skills that employers expect from a PhD holder. One is experience in delivering a scientific project. So this is not restricted to physics. While the second skill is deep knowledge of a specific quantum system and of the latest scientific results, which is restricted to the physics discipline in that sense. The next most common degree and subject was a bachelor's in engineering. One thing that at first appears contradictory in this analysis is that when considering degree subjects, only 57% of companies said that they employed at least one person with a bachelor's degree in engineering, when previously we saw that 95% of companies employed people with job titles of engineer. There are two possible reasons for this. One is to do with the analysis method we used, which only counted cases if the interviewee explicitly mentioned bachelor's engineers, which may lead to some undercounting. The other reason is related to the fact that many of these PhD holders in physics are employed as engineers, for example, as quantum engineers. And I'll talk more about this later. So companies interviewed valued these engineers for their expertise in design, manufacturing, and production of components. For example, one interviewee said, "I don't expect a PhD physicist to be a good person to do a design for an ultra low noise current source. I prefer that work to be done by an electrical engineer who's got a stronger background, because it ends up being cheaper and faster to do it that way." Moving down this graph, we see that smaller contributions to the quantum workforce come from computer science degree holders, as well as chemistry and maths, though mainly those with some research experience at the PhD level. So now we look at what the relationship is between the degrees that current employees have and the jobs that they are employed in. Let me talk you through the interpretation of this plot. In this row here, we have all companies that reported employing someone with a physics degree at the different levels, associate through postdoc. Each colored box corresponds to one company. So for example, we see that one company reported employing at least one person with a bachelor's degree in physics as a technician, 4 as engineers, 4 people as experimental scientists, 1 as a theorist, and 1 as an applications researcher. As we move along to higher degree levels, we see that there are no technician jobs, but the number of companies reporting in all other categories is highest at the PhD level for physics. Here we also see what was mentioned earlier, that some of these physics PhD holders are employed in jobs titled engineer. We also have this data for engineering degree holders. The pattern seen here is clearly different from physics degree holders, with a larger number of companies reporting employing people from the associate's and bachelor's degree levels as technicians and engineers. For computer scientists, while the overall number of employees reporting is lower, there is a pretty even spread across the degree levels, with a bachelor and master degree holders more likely to be employed as software engineers, while PhD holders taking theorist or application researcher jobs. So now, our penultimate question of what new training is needed. The responses to this question from our interviews generally indicated that employers were satisfied with the skills and knowledge of PhD graduates had when they entered the industry. However, we have to keep in mind that many of these jobs are highly specialized and are well matched with specific PhD programs, which companies deliberately recruit from. One specific skill that was generally valued was hands-on experience, epitomized by the experience gained in doing an experimental physics PhD. Employers were looking for similar experience at the bachelor and master's level, cognizant of the fact that the years of experience from a PhD would not be replicated. One theme that arose from the interviews was a desire for engineering students to have some basic knowledge of quantum information systems, partly to increase the speed of onboarding into a company through speaking the same language, but also as a motivator for students to consider jobs in the industry in the first place. This would come in 2 possible forms: a software track focusing on the algorithms and back-end control systems of hardware, and a hardware track and a hardware track about constructing qubits in their various forms. Finally, for physics students, experience with more engineering-like skills, such as working collaboratively on software, or simply engineering and design skills, were often mentioned as desirable. The quantum knowledge of physics undergraduates was valued, though it was noted that few would have any experience with real-life quantum systems and actually getting something to work in a lab. So then our final question is, what are the hiring challenges? So the challenges of hiring are not simply a function of the number of new graduates from higher education programs, but also depend on the demand for skills across the quantum industry as well as other industries, and the situation of each company in terms of its own reputation, geographic location, and network of connections. Therefore, some companies find it easier to hire than others. Some companies reported it hard to find quantum information theorists who have a good understanding of the application of algorithms. For example, a lot of the theory positions have been the hardest. It's very specialized as far as the number of groups in the world that focus on things like quantum computing algorithms or quantum error correction was reported by one company. However, other companies found that less of a problem, and some even didn't find it a problem at all. This might be because theorists are often expected to hit the ground running, being able to fill a specific role, and so fewer candidates are suitable for any given job. This expectation is likely a result of companies not having the resources or economic need to actually train quantum information theorists, and they just want to pick them up off the shelf. Secondly, 29% of companies reported that, and this is one example of what somebody said, what's challenging is finding people with relevant electronics expertise. And by relevant, I mean sort of a good blend of analog and digital. This is because there is less focus on analog electronics in current electrical engineering degrees, because almost everything we do today is digital. So fewer people with these skills are entering the market. Indeed, another interviewee said, you can't find any good analog electronic training anymore. The demand for analog electronics, as mentioned earlier, is due to the need to interact with fundamental physical systems that are not binary. So now I just want to briefly discuss some of our findings. And before concluding, the one thing that I want to mention is some use of terminology and that I've touched on earlier, and that is, what is a quantum engineer? Is it a PhD physicist who's gone into industry? Is it a bachelor's electronic engineer working on quantum hardware? Or is it a software engineer who has some quantum information science knowledge who's writing quantum algorithms? The problem is that it depends on who you ask. And this is a warning that if someone says we need more quantum engineers, make sure you know what they are talking about and what specific skills they are referring to. Are they people with research experience in physics or engineering? Are they people with research experience in physics or engineering experience building low size, weight and power devices? So that's just something to keep in mind. In conclusion, today we've answered the following questions. What are the career opportunities in the quantum industry? What skills are valued? What are the routes into the quantum industry? What new training is needed? And what are the hiring needs? And then we've also provided resources in our paper to identify the relationship between the skills and courses that are currently being taught or are under development. And I provided a link on the right-hand side here again, so you can access our paper. So finally, I'd like to thank the QEDC for their help in recruiting interview participants, as well as Jessica Hain and Mike Veristek for their help in performing inter-rater reliability for this research, as well as funding from the University of Colorado Boulder, Rochester Institute of Technology, and the 2 NSF grants that are on the screen now. Thank you for your time.
Okay, Michael, I'll clap on behalf of everyone who is muted for a fantastic talk. We have plenty of time for questions, and it usually takes people a few seconds to type in their questions, and I often have some of my own, so I'll go ahead and type a couple of mine in while others get a chance to type. If you could, take a look at the chat window.
Yep.
And I just pasted 2 questions.
Okay, so this study wasn't looking at salary information.
Okay.
So there is some aspect of supply and demand. So like on the last slide where I mentioned some of the hiring challenges, people who, so like analog electronic experience is highly valued, and therefore I would imagine demands a higher price. There was one interviewee who mentioned that basically because young people do not necessarily have that experience, they have to pay more for basically older employees who have that experience, who are trained in it. And so that's a premium in the quantum industry. But yeah, because our study was looking at skills and knowledge, we deliberately sort of didn't ask about sort of exact numbers of people and salaries and possibly like commercially sensitive questions, so we could increase our access to these companies. Though the QEDC has produced surveys that are looking more at the sort of quantitative side of the quantum industry. So if a company is a member of the QEDC, they can get access to that data, and it has been presented at other conferences and workshops. And then your second question Yeah, so the needs of the industry do not line up with traditional academic fields or departments. So I think this question of like the interdisciplinary aspect of quantum information science and the quantum industry, it makes it much more complicated. And there's one thing that we discussed at the Kavli meeting about setting up courses and whether universities should try to set up new like departments on quantum information science. And the main challenge there is logistical. And so the recommendation here of engineers having 1 or 2 semesters of training of courses in quantum information science relevant to them is kind of comes out of that, in that the effort of setting up a new institution to study quantum information science is much more sort of a long-term goal, I would imagine, than if we want to have an impact in the short term and immediately, then that would be, it would be easier and quicker to set up these courses in engineering. There's also a recommendation of the Defense Science Board, so the military academies in the US are also being advised for their engineering students and computer science students to set up 1 semester courses in quantum information science as well. So our recommendations align with theirs. Don, was that?
Yeah, I think what I'm getting at is if you look at the modern structure of the university, it's usually departments that are aligned with subject matter expertise in traditional topics. And if you look at the needs in the world, they don't align with that. So if the needs aligned, then your companies would be saying, I need a physicist, a chemist, and a biologist. But that's not what people need anymore. They need people who know a whole bunch of different stuff that cross disciplines in order to answer real questions. And I think some people have asked the question, should universities be restructured to be oriented towards solving problems? And there are pros and cons to that. Because if you're just solving specific problems, then maybe you haven't learned the basic science in the individual subfields. So I see that the approach now that you're advocating is keeping the traditional silo structures, but tagging on interdisciplinary connections, as opposed to flipping it upside down and restructuring the universities for interdisciplinarity, where the individual subject matter expertise is tag-ons.
Yeah, so one of the key things from the interviews was like companies, like almost all the companies basically said one of the key skills they're looking for is the ability to work in a team and across disciplines. So physicists to be able to communicate with engineers and vice versa, so that then you can work with each individual's strengths. So like companies like appreciated that different people, this was a team effort and each individual's brought their own aspects to it. And skills, and that those skills need to be deep, so that then you could actually do something. And so that's sort of where when I presented the broad sets of skills that were valued, the actual quantum information aspects didn't come into it as much, because the other skills that are more traditional are still highly valued for their specializations. But it's just a matter of being able to communicate effectively with those skills.
Okay, thanks. I think Dominique had a similar question. I don't know if that's already answered.
Yeah. So I think it's limited in the cross-disciplinary because they still want an electronic engineer to build circuits, or they still want a quantum physicist to design a setup for qubits. So those skills are distinct, but they have to work together. I'm just looking at the next question. Did you try interviewing companies in the traditional industries? Are they looking at quantum technologies as potential disruptors to their own technologies? So we didn't look at traditional industries because we were looking at the quantum industry as who were producing these products rather than necessarily who was going to be using them, because the use the people who are using them are, because it's sort of like not quite there yet in actually finding uses for them in traditional industries. So that might be a future study, and that's sort of like, I saw David's question there, how do you plan to follow up this work? So future work could be looking at that aspect of it. So, and looking at Jonathan's question, you mentioned in passing something about a company's ability or inability to train new employees, but was there any discussion with interviewees about their possible need for professional certificates, continuing education programs, short courses, etc., for their existing workforce, both for new hires as well as employees with more experience in other fields? Yes, so we did ask that question as well, and that is covered in the paper. So companies did like the idea of retraining their existing workforce. So like, say they, like large companies who have some engineering workforce who want to be moved on into these quantum technologies, training specifically. So one example was they're going to like 1 week training course on how to use a frequency cone. So things like that on specific skills, and mainly to do with like learning how to use specific bits of hardware, so that then you don't waste time and money if you try to break it, or if you do break it. And it was more focused on that kind of thing rather than sort of general courses on quantum information science, because that was quite a few companies said that had less value for their engineers. It was a motivational aspect for their own employees in terms of retraining, being like, this is an interesting topic. Lots of people were talking about it. I want to know more about it. But lots of companies said for the actual, in terms of productivity, they wouldn't necessarily value that as highly as specific courses on specific things that would push their products forward. Saying that also some companies had internal training, like lectures for their employees to bring them up to speed on specific aspects of, say, quantum optics, or other, it's just dropped out of my head, but like lecture course style things that internal training. So for example, like on quantum computing, like internal courses to train the rest of the workforce so they have some familiarity in what it does and what it, so if they get asked by clients, they can sort of mention and not say the wrong things about, say, quantum computers, for example. So I hope that answers your question, Jonathan. And then David, yes, so in terms of following up this work, I mean, there's lots more questions, and at the end of our paper, we have quite a lot of them. It's also a matter that this work was done in fall last year, and so the impacts of coronavirus and stuff on what the workforce is looking for and hiring and progress that's being made in the quantum industry is not been included in this work. It's also a matter of, at this moment in time, which specific hardware technologies are developing fastest, and where those skills will need is an open question. So, and looking at the skills needed in terms of the like programming quantum computers, there's a sort of, lots of the companies were focusing on hardware, with the hope that in parallel developing the sort of algorithm side of things, so that when the hardware is ready, they can actually run stuff. But at the moment, the algorithms is ahead of the hardware, and so but if we looked at the algorithm side of the skills needed there, that would be a different question. But we were trying to ask the question of what does the industry need now, and now the sticking point is getting the hardware there. So I think hopefully that answer gives some insight into what's next.
Okay, Michael, that was a fantastic talk. Thank you very much. We do have time for more questions if anyone has them. If not, then I look forward to seeing everyone tomorrow's talk at 1 p.m. at the regular time. And have a good day, everyone. So long, and thank you, Michael.